Hey, this is Professor Lewis. We're going to talk about welding basics here in just a short lecture just to kind of understand what welding is, how do we call it out, how we inspect it, and where we expect it to break, as well as some of the processes. If you were really interested in welding, where could we go learn further education on this? If you're wanting to get an actual degree in welding engineering, Ohio State, Laterno, down in Texas, they'll have good programs in that, as well as master programs. I've seen some students go to graduate school at Ohio. Another good source of information would be to study up with Lincoln Electric. They have a really good school where they focus on blodgett weldment design. Very good classes to go to. Very in depth and very useful. Um, let's get into this. We're just going to hit some high points. I'm going to be leveraging some slides possibly used from other courses. I'm not going to spend a lot of time because this is short, but there's key things that I want you to pick up. And in the process of welding, the key thing is its fusion. We would like to see some molten weld material being typically added. We would like to see a really good fusion taken on with the base material in the pieces that we're welding together. Now, when we do that, we're going to have what we call a HAZ zone, a heat affected zone right here. And the further we get away from the weld, the temperature goes down, and we're not going to change any of the original microstructure in the base metals. So we can get hot enough that we can actually change the structures near the weld. That may weaken that base material. We could have some mixing of the base material with the weld materials, and later on you guys are going to have a course in machine elements, machine design, and you'll have Shigley's book does a great job of talking about how to calculate the strength of the weld, assuming mixture effects on base material. It goes into a lot of depth there. Really good design. And a lot of his stuff keys off of to the Blodgett methods. If you read his references in his books, he's coming up with the stuff from what Lincoln teaches. Very good content. So we're going to have things happening due to heat in this weld. When we call a weld out on a print, this is just a quick reference drawing of a typical weld call out. We're going to have an arrow pointing to the pieces that we want to weld together. We're going to have a section called the reference line and then a tail. Typically in the tail sections where we're going to designate the process. What are we going to weld this with? Is it stick welding or MIG welding? That's the slang term. We can't put those on a print. We have to use the American Welding Society term. So we'll be talking about some of that as well as some of the reference symbols here and how to apply them. Probably the reference symbol that we're going to use in this class and that all I really care for you to know about is the fillet symbol right here. There's a lot of other symbols that we can put on that reference line as well as some modifiers or supplementary type symbols. If we're going to weld all the way around something, we'd put a circle around that symbol right here. But we're just going to do typical fillet welds. And this is a picture of a call out for a part where we're pointing here, and it just demonstrates the sides that we're going to weld on. So here's the arrow, here's my reference line. If I put the symbol on the bottom side of the reference, then that means the side that I'm looking at. If I put that symbol up here on the top, it would be the other side. This 1/4 inch is going to be a reference in terms of the leg, the size of the weld. Now, this is a neat little slide I put in here because we can have different size or legs of welds on different sides, for example. And so here we could call them out. Again, these call outs typically, if they're going to be the same on the whole weldment, we might put it in the notes that all welds are going to be 1/4 inch unless otherwise specified. And then it saves you from having to type it in there time and time again. Now, let's look at some terms. We've got the leg of the weld. That's the distance from here to this far point, which is the toe. That's going to be our leg of the weld. It's typically where we measure the welds. So 1/4 inch, 1/2 inch, 3/16, things like that. We're going to draw a line from toe to toe, from right here to here, and then a line right here that comes at 45 degrees is going to be our theoretical throat, the effective section of that weld. And so what we're saying is basically that if we're going to break this weld, this is where it's probably going to break at, is across that theoretical throat. And so we're really interested in that throat size and inspecting that. We're also interested in the depth of diffusion on this. So again, we're going to be looking at maybe how the material, the heat from the fusion, the weld ties into these, and that we don't have any cracks or overlapping of the materials as well. Now I'm going to go ahead and skip this little slide down here and get to this slide. We're going to use a fillet gauge, and hopefully it'll go slower here for us. A fillet gauge is a series of gauges that we can measure the convex and concave features of a weld. Here we're going to come in here and check this, and we're going to see that the fillet weld measures 3/8 here. Okay, and that's looking really, really good. We're going to come in here and check the other leg as well. So that was leg 1, and so now we want to check leg 2 with that gauge. So we're going to come down and make sure it fits good on the metal and we're going to check and draw a line, and it looks like our legs are good here. The next thing we're going to do is come in and check our throat of this weld. And so the other side of the gauge that has 3/8 has this raised portion. We should be able to come in here with it lined up here and make it contact, and it should touch the weld, and we know we have a good weld there, okay, that our throat is a 3/8 weld. Inspecting the welds, we want to do a quick visual for that porosity in the weld. We want to think, did we have shielding gas? Here's a nice weld. Here's a weld without shielding gas, and these little porosities that get in the weld are going to cause defects and make the weld break. Now this is a multi-pass weld, and we had issues with gassing at each pass here. Now let's talk about the two processes that I expect you to know for this course. The first one is going to be SMAL, shielded metal arc welding, okay, SMAL. And so the acronym, that's where we would put it on the tail, is SMAL. And that, now a lot of you guys are going to call this stick welding, okay, that's the slang term, stick welding. We're using a rod, and a lot of times we can change the wire diameters or the coatings that go on the, here we'll have a cellulose fiber, and we want to keep those fairly dry. And they may put additives in there, different metal additives to make them stronger or weaker. So here's a 70-18, here's a 60-11, 60-10, and we can put different additives in these cellulose fibers and coat that rod. And that will burn off, making a very robust protective atmosphere around the weld. So this process is really good for outdoors. This is our stinger that we're going to put a rod in, and then come in here, and this consumable, this electrode, is going to disappear as we weld. So shielded metal arc welding, SMAL. Now real quick, I just threw this up here. They're going to talk about the rods in terms of identification systems. On a SMAL rod, they're going to have an E, maybe 2 digits right here. These are the most important for us. That's the tensile strength, 60 KSI. So if we had a 70-18 rod, the 70 would indicate 70 KSI. Now these others go into welding position, currents, and other things that we would do if we were in a heavy welding course. We'd expect you to know all the combinations of those as well. But right now, just the 60 and the 70s are going to be of importance, the strength. Now, if we change from a leading to a trailing type angle as we move across a weld, we can be pushing. There's going to be force going on here, and we might get a thinner penetration weld. So if we're welding with thinner materials, stuff like that, we can actually change how deep the penetration that we're going to get on this versus our lead angle. Likewise, the trailing angle, we can really get some more depth on the angle on here. And again, the weld's going to push up and stack up a little bit more. So a welder is going to know how to do those kind of things and be trained in it. Another thing they're going to do is learn how to do different kinds of patterns. And I just put a simple weave pattern on here, where sometimes they just do an elliptical type shape, and maybe it's a little tight and a little bit looser, and that's going to change the depth of the penetration, how the welds tie in, and all that. And they're going to be watching those welds, seeing what happens. Let's get into our second welding process. Now this is GMAL, gas metallic arc welding. A lot of you guys are going to reference this as MIG. MIG is the slang shop term word use of it. And it's acceptable to say that in companies, but when I put it on a print or I'm doing specifications, I need to use the American Welding Society designation. This is where we have a wire that's going to come through your leads, and it's going to have a contact tip where we can transfer the electricity to the wire, and we're going to come in here and melt that. There's different transfer rates and stuff, methods that we can go in there, really neat stuff. You're going to have gas, shielding gas, that's going to come through here and be released around this nozzle tip to provide a protective atmosphere. Again, we don't want oxygen interfacing with the melted metal puddle that we have going on. This is not as robust to do outside. This is more of an indoor type process. It's going to be a lot prettier looking weld, okay? And there's a lot of disadvantages and advantages to each process. Again, we don't have time to go through all that because there's a lot there on the table. we're going to have the electrode carrying our current coming through here. Now this is a picture of an example of a machine where we'd have the wire coming off here decoiling with a feed mechanism. We would have a bottle back here with a regulator. The electricity is being transferred through these leads. Everything is going to go to the leads going down to the weld. And again, you're going to be able to change all your parameters with the machine in terms of what volts and amps and wire feed you want to have running. Do you want it positive, negative? There's a lot of neat stuff there as well. Let's see here. The filler rods on this, they're going to have an ER, so electrode rod, and the 70 representing the, again, minimum tensile strength of that weld filler rod that we would have on there. And that's gas metallic arc welding, GMAL. Here's our feed mechanism where we can come in here and lock these feed mechanisms and push that wire through there. It just kind of gives you a close-up of that mechanism. Let's talk a little bit about shielded gas. Now, if you're going to be welding in a weld shop, you're probably going to have to do a full-on high-pressure bottle training before you ever weld, because these things are up to 3,000 and 4,000 psi. And if you knock this head off this bottle, or you open this valve stem and you're standing in the wrong place, these regulators, these can have tendency to break over time with the impact that pressure hitting, or if somebody hit it or something, for example, dropped it when they were changing bottles and didn't realize they put a small crack in it, and then when it hits that high pressure, these things can pop off and do serious energy or injury to you. They've even had bottles get knocked over and go through solid concrete walls. So this, you would really need to talk about how you deal with bottle safety. Looking at the gauge here, this is going to be our pressure gauge. This is going to be our flow rate gauge. They're going to know how much gas, and they measure that in cubic feet per hour. Now they're going to have all different gases that they're going to put out there, and the bottles will be properly labeled. Looking at the gases, we might, and I just wanted to throw something out there. A lot of times we use argon. That's going to have a narrow type but fairly good penetration. The best gas I like for penetration, deep penetration, is going to be the CO2. It's going to have really deep, robust penetration. It's going to have splatter though. But you're saying, why are you putting oxygen in there when we're trying to protect it from oxygen? This amount of oxygen in the CO2 is just enough to help promote arc growth and make a hotter weld. There's a lot to this stuff. Argon mix may be really good for better penetration and look a lot better, and not require a lot of cleanup from the splatter. Now, before we weld a piece of material, let's talk about our base materials. Typically, we get steel that's hot rolled steel. It's going to be probably an A36 for a lot of the steels, and especially what we're doing here in lab. And it's going to have a mil scale on this sample. If I look at this right here, I could see mil scale on this sample right here, and that can flake off, and that's an oxide. That is an insulator. We don't want to try and weld across that and get that broken up into the weld or anything of that nature. We want to come in and maybe grind with a flap grinder or a belt disc. If we're going to weld on this surface, get rid of that mil scale. Here's a part that didn't have the mil scale removed, and when they welded it, it actually looked like a nice weld, but look at it. We loaded it just very lightly, and it just broke off because it couldn't get fusion in that side of the weld. Again, kind of a crack showing here. Still no real depth of fusion on there. Might look like a nice weld, but we need to load it and see what's happening. Here's what we want. We want some fusion, some depth of fusion in this T-weld here. Now, you're saying this looks kind of like a crazy weld. I threw this up here because if we're looking at it, I can see that here we're welding along, and then it kind of changes here because look at the width of the puddle here. The welder that did this started going wider here, was narrower here, and it did break across the throat. Here's where they stopped, and when we stopped, there could be a crater, and that could become an issue with maybe potential breakage. So we may want to look at the broken part and see where did we think it cracked and broke and started from. But we want a nice consistent weld. This is not consistent all the way across, but it did break, and we did get good fusion where this one would not, okay? It would never break the weld across that theoretical throat. Here we have, if you're going to go to a company, let's say you hire a welder and they came from Tulsa Welding School, great school, nothing against them. It's just if you're at Ditch Witch or Caterpillar or some other company, McElroy, and you're going to hire them to do welding for you, you have to test them in your process at your facility to certify them. And so this is a typical test that they'll do. They'll have it written up and everything in long form. The welder will have to set up the machine. They'll have to conduct a series of welds like this, and then load it in a machine where we just come in there and press it, and they can use a standard shop press for this and see where the weld breaks and how much load it held, for example. And here we had a nice weld break across the throat here, so this would be a good weld. And you can see the weld looks really nice there. Let's talk about a term, fixture and jig. What's the difference between fixture and jig? Fixture locates the parts, and that's it. A jig will locate the parts and guide the tool. So when we're going to do a weldment, we make weld fixtures, not weld jigs. And a weld fixture like this is going to locate the parts, and this one is a tack-up fixture where we can come in here and tack these parts up and hold them in place and then weld them. Now, I didn't weld this part. I just put it in the Templin grips here to show you how we can test this, where we can pull that top and bottom and pull that weld in shear. So again, in this course, we're going to talk a little bit about 3 different testing methods. We're going to look at shear, bending, and torsion. Those are 3 simple equations we've learned in strengths and dealt with. Force over area, MC over I, TC over J. You guys know those equations, and it's not that hard to apply to weld design. So we're going to see some of that. Now then, here's a bending fixture where we can come in here and tack this up, and then maybe we're going to slide that sample in here where we could now come in here and push on the end. And maybe we want to look at, is it better to weld on the top and the bottom, or is it better to weld on the 2 sides? Now somebody's going to say, well, just weld all the way around. The problem with that is deposition, time to manufacture that part. If just 2 welds would hold that part, that's all we want to do. We don't want to weld all around unless it's just cosmetic and the customer's going to pay for that. So we're going to be able to design this and see what's the correct placement and size of the welds there. Torsion. This is a torsion fixture. We're going to locate our parts, come in here and tack it up, and then weld it. And again, do we want to weld on the sides or on this end and the other side underneath? And again, we're going to put it in a fixture and testing fixture and come in here and load that part and hopefully break it and see what happens. Now then, I've mentioned a little bit about the heat, and the welder can see something. This is where we've captured some video for you and leveraging some other people's stuff here, where we can come in and talk about the welds and the quality of this. And so what we're going to do is come in here and watch this weld as we go across here. You can see it's kind of irregular and a lot of splatter, and it was just all over the place. And that's the part that we got. That's not a very pretty weld. That's not going to test good. Okay. Now the next one we're going to watch, and that's just that same one there. I probably need to hit, there we go. Let me get back to the beginning here of this one. Let's watch this weld. This is going to be more a consistent and better weld going across here. And see how the heat is tying in to the tops and bottoms, and you can see it cooling off the slag off here. And this is going to make a lot nicer weld here on this part. And so we would go in there and then test that weld. So the welder is going to be trained, and it takes a lot of experience to do that stuff. It's something we can't just take you guys out and do this. We do have a welding certification program that you guys can go out there and get weld certified, and you're going to spend lots of hours out there, more than what we have time for this course. And this course is not so much welding, more of testing of weldments and a little bit of the calculations that go into that. So for this one lab. So weld defects, man, things like overlap. Did the weld overlap and not fuse in here? Did we undercut? Is that going to be a source of it to break? Did we get improper fusion? The travel rates, all these kind of things. There's a lot to weld inspection. You may have to have x-ray, ultrasonic equipment, things like that. So you would really want to study up on the weld quality. So hopefully this covers the basic weld portions. I think the next video we're going to have is a little bit about the equations and the analytical, some basics of those 3 designs that we talked about: shear, bending, and torsion.